Okay, let's unpack this. Sometimes just one single event, a breakthrough that seems almost impossible, it just fundamentally changes everything. We're talking about those rare before and after moments that completely redefine what's possible. Not just in tech, but like in how we see the world.
Exactly. Like the printing press or penicillin, they weren't just inventions. They completely opened up new ways of doing things.
Totally. And today we're diving deep into exactly one of those moments, a pivotal shift that didn't just nudge a field forward, it really ignited a revolution, the ImageNet moment of 2012. This isn't just a story about some competition, it's a whole narrative. There's a deep neural network, this really ambitious challenge, and a breakthrough so big it truly sparked the whole deep learning revolution.
Yeah, it wasn't just a win. It was like a massive wake-up call. It completely changed the path AI was on.
So what's our mission today then? What are we trying to figure out here?
All right, so our mission is really to get under the hood and understand why this specific breakthrough was so incredibly significant. We'll dig into the how behind it, the technical stuff, including the absolutely crucial role played by powerful computing hardware like GPUs. We can't forget those.
Okay, GPUs are key.
Definitely. Then we'll sort of connect the dots, see exactly why ImageNet became this spark that convinced, well, not just academics, but really the whole world, that deep learning could actually solve problems people thought were impossible. What's really fascinating here isn't just the amazing technical achievement itself. It's the massive shift in perspective it caused.
A shift in perspective, how so?
Well, it basically forced everyone in AI research and development to completely reevaluate stuff they'd considered impossible for decades. Suddenly it was like, wait, maybe we can solve this now. It was totally unexpected for many.
And here's the kicker, right? Whether you consciously realize it or not, the ripples from this single moment, they're felt in the AI you interact with, like every single day.
Oh, absolutely. Every day.
Your phone unlocking with your face, those movie recommendations, search results, it all owes a huge debt to what happened back in 2012. So yeah, get ready for some pretty surprising facts, a journey through some cool tech innovation, and a real deep dive into the foundations of the AI that's shaping our future right now.
Okay, so to really get the scale of this ImageNet moment, we kind of need to rewind first. Let's paint a picture. What was computer vision actually like before 2012? I mean, what made just identifying objects in pictures so incredibly hard for machines?
Right.
For us, it feels so natural, right? You see a crumpled paper, a specific dog breed, you just know.
Yeah, you've hit on a core challenge there. It really is a whole different ballgame for computers. Our brains, they process visual stuff with this incredible, almost unconscious speed and robustness. We see a cat, right? Doesn't matter if it's in bright sun, deep shadow, close up, far away, partly hidden.
We still know it's a cat. Exactly. We generalize effortlessly. But machines, historically, they struggled massively with that. For ages, trying to code that kind of intuition into rules or algorithms was just extraordinarily hard. A grand challenge for AI, really.
So what was the specific difficulty? Was it just the sheer amount of visual data?
Well, think about the complexity of just the raw visual input. Norbert Wiener, back in his work Cybernetics, pointed out that our brains don't just see pixels. We focus, we abstract things down to outlines, key features. Then we compare those simplified bits to this huge mental library of standard impressions we built up, circle, square, cat shape.
Makes sense.
Early machine vision had to try and copy that, but without any of the built-in biological intuition. Yeah. And then you add the world's variability, lighting changes, different angles, scale, cluttered backgrounds.
Right. The same chair looks totally different from above versus the side, or in shadow.
Precisely. A slight change could make a recognized object look totally alien to a traditional algorithm, just a jumble of pixels it couldn't place. That was the fundamental hurdle they were banging their heads against.
Wow, okay. Sounds almost impossible, especially when, like you said, even we sometimes find it tricky, right? Telling apart really similar things. So what was the human benchmark for this ImageNet task? How good are we at telling apart, say, two similar dog breeds or different kinds of locks across 1,000 categories?
That's a really crucial point, setting that baseline. Because even for humans, perfect scores across 1,000 diverse categories, not happening. The ImageNet task, it involved classifying objects across, 1,000 distinct categories. And research showed that humans doing this exact task typically made mistakes about 5% of the time.
5% error rate for humans. Okay.
And these weren't always easy calls like you suggested. We're talking really fine-grained stuff. Telling a Tibetan Mastiff from a Bernese Mountain Dog, they look kind of similar, right?
Yeah, definitely.
Or telling a heavy-duty safe from a combination lock. You need to pick up on subtle visual cues. It requires deep understanding, even for us. So that 5%, that was a seriously high bar for any AI system to aim for.
Okay, so humans, with all our brain power and experience, still mess up 5% of the time on these tricky distinctions. Given that high bar, how were the machines doing before this big moment, say back in 2010? Were they even close?
Close. Not even slightly. The gap wasn't just big, it was, honestly, enormous. A huge chasm. In 2010, just 2 years before the big breakthrough, the best machine predictions in the ImageNet challenge, they were making mistakes on a staggering 28% of images.
28%. Wow, that's almost 1 in 3 wrong.
Exactly. It wasn't just a small shortfall. It was a loud, clear signal that the traditional ways of doing computer vision were hitting a serious wall, a performance ceiling they just couldn't seem to break through. Like some sources say, progress in practical AI had been really slow for a long time, just incremental gains. Nothing suggesting a massive leap was coming.
So there was maybe a bit of pessimism creeping in.
Definitely a sense of frustration, maybe some skepticism, a feeling that something totally new was needed if AI was ever going to get close to human-level vision. That 28% error rate was just a stark reminder of how huge the challenge still was.
Okay, so that's the scene. Slow progress, this massive gap between human and machine performance, a problem feeling almost unsolvable with the old methods. Against that backdrop, let's get specific now. What exactly was this ImageNet challenge that turned out to be so important? What made it different?
Right, it was definitely more than just your standard academic contest. ImageNet became this really high-profile annual contest to predict the name of an object in an image. What really set it apart was its sheer scale and, like we touched on, the incredibly fine-grained nature of the task. The dataset was huge, 1,000 distinct object categories.
1,000 categories, that's massive.
It is. And again, not just easy stuff like car versus apple. It demanded these really nuanced distinctions, like telling specific dog breeds apart, the Tibetan Mastiff versus the Bernese Mountain Dog example, or differentiating a safe from a combination lock.
So incredibly subtle differences sometimes.
Exactly. It wasn't about simple pattern matching. It required a deep, almost semantic understanding of visual features that computers back then just really struggled with. The complexity really pushed the boundaries of what people thought machines could do.
So the goal wasn't just, is it a dog, but is it this specific breed of dog? Out of 1,000 possibilities, that sounds like it needs almost human intuition. How did they even quantify that for a machine to learn?
That's precisely the point.
Yeah.
The competition basically forced researchers to build systems that could pin the right label on an image from this huge, complex list. It really challenged the limits of statistical pattern recognition at the time.
Statistical pattern recognition. What does that mean in practice here?
Well, at its heart, pattern recognition is about making the best possible guess, right? Which category does this image belong to? Technically, you could think of it as maximizing the posterior probability,
Okay, meaning
meaning the machine's confidence score. After it's processed the image, how confident is it that this specific label out of the 1,000 options is the right one? The goal was to minimize mistakes by always picking the label with the highest confidence score.
got it.
But ImageNet didn't just want any guess. It demanded really accurate, nuanced guesses. It forced the AI community to tackle the deep subtleties of vision head-on. This pushed them to develop models that could learn and generalize from tons of varied image data, way beyond what older algorithms could do. It drove innovation towards systems that could actually pick up on those fine-grained differences.
Okay, we've got the struggle, the slow pace, the wall AI seemed to be hitting. Now, boom, 2012, the stage is set, stakes are high. And then something totally extraordinary happens. The ImageNet moment. What was it? What actually broke through that wall?
Right, 2012 was just this undeniable turning point. You can almost imagine the tension, decades of slow progress hitting that wall. And then Geoffrey Hinton's team from the University of Toronto steps in. And they didn't just tweak the old methods. They came with something fundamentally different: deep learning. It was the first time contestants seriously used deep learning in the ImageNet challenge.
First time, so it was a totally new approach for this competition.
Pretty much, yeah. It was a radical departure from the traditional methods that had only shown those slow, incremental gains. Hinton's team, with their deep neural network, specifically one called AlexNet, they weren't just another participant. They were bringing a bazooka, to a knife fight,
Yeah.
showcasing the power of this tech that many had maybe underestimated.
AlexNet. Okay.
The results just hit the community like a lightning bolt. Instant excitement and the beginning of a huge paradigm shift.
Okay, you said traditional methods were stuck around 28% error in 2010. So what did Hinton's team with AlexNet and deep learning achieve? How big was the jump? Was it just a bit better or really revolutionary?
Oh, it was utterly transformational. They didn't just edge out the competition, they absolutely crushed it. They essentially halved the error rate.
Halved it. From 28% down to...
Down to around 14%, maybe even a bit lower in some measures.
Huh.
This was just unprecedented, way beyond what anyone expected based on how things had been going. It wasn't incremental, it was a quantum leap.
Wow.
To really get the significance, think about that analogy with fraud detection. Going from 98% accuracy to 99.9% sounds tiny, right?
Yeah.
Just 1.9% gain.
Yeah, seems small on paper.
But it means the number of mistakes, missed fraudulent transactions, drops by a factor of 20. That's huge. It makes the system vastly more reliable.
Yeah.
The ImageNet results showed a similarly massive reduction in errors. It demonstrated a capability that was almost unimaginable just years before. It completely changed the conversation.
So way more than just a win in some academic contest. It had much bigger ripple effects. Shook the whole field.
Absolutely. The ImageNet moment wasn't just about computer vision. It flat out convinced the world that deep learning could tackle problems people had basically given up on, thought were impossible for machines. Remember how AI progress had been slow and steady? This breakthrough provided hard, undeniable proof of deep learning's power and scalability.
Tangible evidence.
Exactly. It showed deep neural nets weren't just theory or niche academic tools.
Ugh.
They could get state-of-the-art, revolutionary results on a really complex, real-world challenge that had stumped everything else. This one event shifted the whole mindset. It was like decades of slow progress got compressed into one giant leap. It kind of taught us that sometimes the simplest solutions are the deepest ones, you know.
Yeah, nice one.
It just opened the floodgates. Suddenly, there was massive investment, huge research interest in deep learning. It truly ignited the revolution we're still living through today.
Okay, that's the perfect setup for the next big question. What is this deep learning that pulled off such an amazing feat? We hear the term all the time now, but what does it actually mean, especially in this context of seeing and recognizing images?
Right. So at its core, deep learning is this scientifically inspired approach to machine learning, featuring layered structures that progressively represent more abstract concepts. That's how Yoshua Bengio, one of the pioneers, puts it. Think of it like stacking filters on top of each other. Each layer learns to spot increasingly complex patterns in whatever data it gets from the layer below.
Layered structures. So the deep part is about having lots of layers.
Exactly. The deep refers to neural networks with multiple hidden layers, sometimes hundreds sandwiched between the input and the output. These networks can have millions, even billions of connections or weights that get adjusted during learning.
Millions or billions. Wow.
Yeah, and this deep hierarchical structure is key. It lets the network learn these progressively more abstract features. Simple stuff at the bottom layers, more complex concepts built on top in the higher layers. This is totally different from older, shallower networks with just one or two hidden layers, which just couldn't handle the complexity of real-world data like images very well.
Okay, so depth is key. And you mentioned a specific type for images. CNNs.
Yes. Convolutional neural networks, or CNNs, they were a massive innovation for image recognition. They cleverly exploit this basic property of images. Nearby pixels are usually related, right?
Right.
Part of the same object or texture.
Makes sense. A pixel is usually similar to its neighbors.
Right. So instead treating every single pixel independently, which is super inefficient, CNNs use these things called convolutional layers. You can imagine them like little scanning windows or filters that slide across the image.
Scanning for what?
They look for specific, simple, local features like an edge, a corner, maybe a certain texture, just small patterns. This filter finds these simple features everywhere in the image.
Okay, so it finds all the edges and corners first.
Kind of, yeah. And then crucially, the information from those simple features gets merged in later layers to detect higher order features. So edges and lines combine to form shapes, shapes combine to form parts of objects, and those parts combine to recognize the whole object.
Building up complexity layer by layer.
Exactly. If you picture the data flowing, input image, convolutional layer, subsampling layer, which simplifies things a bit, a convolutional layer, and so on. You see this hierarchy, simple features to complex objects. It mimics how our own visual system seems to work, in a way.
That makes a lot of sense, how the layers build understanding. But these deep networks, especially CNNs, they need to learn, right? How do they adjust all those millions of connections to get it right? What's the actual learning mechanism?
Right. The learning part is crucial. The magic, if you like, the engine that drives the learning in these deep networks, is a really elegant algorithm called backpropagation.
Backpropagation. Okay, heard of it. How does that actually work, conceptually? Adjusting millions of connections sounds incredibly complicated.
It sounds it, but the core idea is surprisingly intuitive. Backpropagation is basically the algorithm that figures out how to spread the learning, the adjustments, back through the entire network.
Spreading it backwards.
Yeah. Imagine the network makes a mistake at the output layer. Say, it calls that Bernese mountain dog a Tibetan Mastiff again. Backpropagation calculates how much each connection in every layer contributed to that final error.
So it figures out who's to blame?
Sort of, yeah. It assigns blame or contribution, tracing the error backward from the output layer all the way back towards the input layer. Then, it makes tiny adjustments to the strength of each connection, each weight layer by layer going backward to reduce that specific error next time.
Ah, and
Yeah.
so it corrects itself by working backwards from the mistake.
Precisely. And you repeat this process, make a prediction, calculate the error, propagate the error backward, adjust the weights millions and millions of times using vast amounts of training data, like all those ImageNet images. Over time, the network gradually refines its internal settings, getting better and better at making accurate predictions. It's like this massive iterative tuning process across the whole network.
That's clever. Who came up with that? Was it new in 2012?
Actually, no. The basic ideas were developed independently back in the early 1980s by researchers like David Rumelhart and Paul Werbos. But it wasn't until the early 2000s, when computers started getting more powerful, that people like Yoshua Bengio really started applying it effectively to bigger problems, laying the groundwork for its huge success later in things like ImageNet.
Right, the computing power. Which brings us back to GPUs. Even with a clever algorithm like backpropagation, adjusting billions or billions of connections, doing all that math, it sounds computationally insane. How vital were GPUs in making this practical?
Absolutely vital. The computational demands were, and still are, just astronomical. Training these networks involves optimizing all those parameters, sometimes trillions now, for big language models. Backpropagation requires tons of calculus, calculating derivatives to figure out how much to adjust each weight. The number of calculations grows incredibly fast with the size of the network. Doing this on traditional CPUs, the main processors in computers, would just take forever. It would be computationally prohibitive, totally impractical.
So CPUs couldn't handle it.
Not efficiently, no. Think of a CPU like a very smart professor, great at complex tasks one after another. A GPU, a graphics processing unit, is more like a huge classroom full of students, each doing a simple calculation simultaneously.
Parallel processing.
Exactly. GPUs were originally designed for video games, rendering complex graphics in real time, which requires doing many simple calculations in parallel. That same parallel architecture turned out to be perfect for neural network training, where you need to perform similar calculations on millions of weights at the same time during backpropagation.
So GPUs massively sped things up.
Dramatically. They took training times down from potential months or years to just days or weeks. This acceleration was absolutely critical. Without the rise of powerful, relatively affordable GPUs around that time, the deep learning revolution and the ImageNet moment itself would likely have happened much, much later. The hardware was the essential accelerator that made the theoretical breakthrough practical.
Okay, so ImageNet, fueled by deep learning, backpropagation, and crucially, GPUs, proved machines could see and learn in totally new ways. It unlocked these incredible capacities. But let's bring it to today. Beyond the academic win, where do we actually see the impact, the descendants of that 2012 breakthrough in our everyday lives?
Oh, the impact is truly pervasive now. It's everywhere. ImageNet didn't just change computer vision. It showed deep learning could tackle whole new classes of problems people thought were only for humans. It opened the door to predicting things far beyond just, say, credit scores or warehouse inventory. Suddenly, complex tasks like object identification, really good language translation, even complex scientific stuff like drug discovery,
Yeah.
they became feasible for AI.
Drug discovery, really?
Yeah, it's amazing. There are examples, like those mentioned in The Singularity is Near, where machine learning, building on these deep learning principles, has been used to find powerful new antibiotics. That kind of thing could be life-saving, especially with growing antibiotic resistance.
That's incredible. From telling dog breeds apart to finding new medicine, so it's definitely not just stuck in research labs anymore. Can you give more examples of how deep learning is just around us now?
Oh yeah, it's deeply integrated. Deep learning has really come into its own, and yeah, it is everywhere. You probably interact with deep networks dozens, maybe hundreds of times a day without thinking about it.
Like what?
Okay, think about your daily routine. You scroll through Instagram. A deep network is deciding what you see first in your feed. Ask Google to translate something. Deep learning gives you that translation almost instantly. Netflix suggests a movie.
Deep learning again.
Yep, a deep learning recommendation engine. Use Face ID on your phone. That's a deep network scanning your face. Even getting a speeding ticket from a camera that reads your license plate.
Uh-oh. Deep learning there, too.
Often, yes. A deep network reads the number plate.
Yeah.
All these things, from entertainment to security to, well, speeding tickets, are direct results or evolutions of the capabilities demonstrated back in 2012. And when you look at the huge buzz around things like ChatGPT now, these large language models with trillions of parameters, they're essentially the great-great-grandchildren of those early neural network ideas building directly on the success kicked off by ImageNet.
It really is staggering how fast it's become part of the furniture, almost invisible. But is it just making things faster or more accurate, or is it changing how we work? Is it augmenting what humans can do?
That's a really important point. Increasingly, it's about augmentation, not just replacement. Yes, AI makes things efficient, but its improved prediction abilities are fundamentally helping humans do their jobs better, tackling complex problems collaboratively.
Like in medicine, maybe?
Exactly. Take radiology. A big part of a radiologist's job is looking at scans, X-rays, MRIs, finding subtle abnormalities. AI systems now can often perform that prediction task, identifying potential issues in images, sometimes with human levels of accuracy or better.
So does that mean we won't need radiologists?
Not necessarily, no. It's more like the AI becomes a powerful assistant. It can screen images incredibly fast, flag potential issues consistently, augmenting the radiologist's skills. Think about deciding whether a patient needs an invasive biopsy for a suspected tumor. An AI's accurate prediction from a scan could provide vital early information, maybe helping avoid unnecessary risky procedures. The AI handles the high-volume prediction, freeing up the human expert.
What does the human radiologist focus on then?
They can focus on the really complex, ambiguous cases, integrate the AI's findings with the patient's history, handle the ethical considerations, and crucially, communicate with the patient. It becomes a partnership, leading to potentially better outcomes and a more efficient system. Human expertise combined with machine intelligence.
Right, so ImageNet opened these doors to amazing capabilities, changing our tech and our lives. But, as AI gets more powerful, more integrated, more autonomous even, what are the new things we need to think about? What are the challenges or, I guess, the flip side of all this progress?
That's absolutely the critical question now, isn't it? This incredible power, while offering huge benefits, it definitely comes with big responsibilities and, yes, real risks. As AI gets more capable and widespread, the whole conversation around responsible regulation and making sure humans stay in control, maintaining human agency, becomes just paramount. You see leading researchers like Yoshua Bengio and Stuart Russell really pushing for this, calling for proactive governance and ethical frameworks.
So thinking ahead before problems arise.
Exactly. There's this growing awareness that we need to think carefully about potential misuse, about unintended consequences like bias creeping in, or weird interactions we didn't foresee. It's not just about can AI do something, but should it? And how do we guide it safely and ethically? And it's not always about AI being too smart either. Sometimes the problems come from its limitations.
Limitations? Like how?
Well, think about social media content moderation. That's a huge challenge highlighted in AI snake oil. Even with advanced AI, systems struggle with the nuances of human language, culture, context. They make mistakes, sometimes blocking legitimate speech, other times failing to catch harmful content.
Yeah, we see controversies about that all the time.
Right. It shows that even powerful AI isn't perfect, and its flaws, its lack of real human understanding, can cause very real, large-scale problems, especially when deployed to billions of people.
That makes sense. Are there other unseen costs?
Well, there's the environmental impact. Training these massive AI models, especially the huge ones we have now, takes an enormous amount of computational power.
Which means a lot of electricity.
Exactly. The energy consumption and the resulting carbon footprint are becoming significant concerns. Some research suggests training a single large model can have a carbon footprint comparable to several cars over their lifetimes.
Wow, that's substantial.
It is. It's driving a lot of research now into making AI more energy efficient, finding better ways to train models, using greener data centers. It highlights that the sheer scale of computation needed for these breakthroughs has real-world environmental implications we absolutely have to address.
So it's clear this isn't a finished story. It's constantly evolving, amazing progress, but also these complex ethical, social, environmental challenges popping up alongside it. The learning journey continues for AI and for us.
Absolutely. Deep learning is incredibly dynamic. New models, new techniques, new applications are appearing constantly, all building on those foundational moments like ImageNet.
Yeah.
And it reinforces that idea, doesn't it, that there's always more to learn and that hearing different perspectives, understanding the technology and its impact is crucial. It's this ongoing conversation between human ingenuity, machine capability, and our societal values,
Yeah.
constantly pushing boundaries.
So we've really covered some ground. We went from this seemingly impossible task teaching a computer to truly see to this single game-changing event in 2012, the ImageNet moment. It just rewrote the rules, launched us into this era where AI is everywhere, in our phones, our social feed, changing industries, helping humans do amazing things. It really was a spark, wasn't it?
It truly was. And reflecting on that, it makes you wonder, doesn't it? If one competition, one specific moment, could so dramatically shift our whole understanding of what AI could do, what machines could learn, what seemingly unsolvable problem out there today is just waiting for its own ImageNet moment. What huge challenge is maybe just one breakthrough away from having its boundaries completely redrawn, expanding what we believe is possible all over again?
That's a really powerful thought to end on, something for all of us to think about, and definitely a reason to stay curious, keep asking questions, and stay plugged into where AI is heading next. Thanks so much for joining us on this deep dive.